Good morning, students. Today we are going to see about Chapter 5, Magnetism and Matter. In that, first we are going to see the properties of a magnet. Properties of a magnet for some common basic rules regarding the magnetism. So the Earth itself behaves like a magnet with magnetic fields pointing towards the geographical north and south pole. Geographical north and south pole. If you tie a magnet freely in the atmosphere, means it points north and south direction. Their ends points towards north and south direction. Wherever we are going to tie, it will be on north south direction only. So the geographic north is called the north pole, and the geographic south pole is called the south pole of the magnet. South pole of the magnet. When two north poles if you bring two north poles together, means it will be a repulsive force. Similarly, if two south poles comes together, means it will be a repulsive force. If you bring a north pole and a south pole together, means there will be an attractive force, that is opposite poles attract each other. Similar poles repels each other. Similar poles repels each other. If you are taking a bar magnet and one end is of north pole and another end is of south pole, and if you break that magnet into two parts, means it won't becomes as a north pole and south pole. The broken end will becomes as on other pole, whether it is north pole or south pole. Either it is north pole or south pole. And it becomes as a single magnet. So this property is called as magnetic monopoles do not exist. That is, magnetic monopoles doesn't exist in the magnet. And it is possible to make magnets out of ions and its alloys. Out of iron and its alloys. So these are the properties about the magnetism. Basic properties about the magnet and the magnetism. Now we can see about the magnetic field lines. Properties of the magnetic field lines. How the magnetic field lines behave. So the magnetic field lines of a magnet will not be a straight line or a curved line. It will be a continuous closed loop. Continuous closed loop. These field lines begin from positive charge and it is going to end at the negative charge or escape to infinity. Escape to infinity. It will be a closed loop, continuous closed loop, and the field lines begins from positive to negative charge. And if you are going to draw a tangent to the field line at a particular point, mean it represents the direction of the net magnetic field B at that point. Net magnetic field B at that point. And the larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. B is larger around around these two regions. So the larger the number of magnetic field lines crossing per unit area. If you are taking a unit area in the magnetic field lines, then the number of field lines is greater, means then the magnitude of the magnetic field will be stronger. Magnetic field will be stronger. Then the magnetic field lines do not intersect each other. They travel parallel to each other. Magnetic field lines are parallel to each other. So and the direction of the magnetic field would not be unique at the point of intersection. So these are the properties about the magnetic field lines. Then we can go for the Gauss law. So this Gauss law is for a closed surface. This Gauss law is for a closed surface represented by the number of lines leaving the surface is equal to the number of lines entering it. If you are taking a closed surface and we are going to find the magnetism in that, means for a closed surface represented by the number of lines leaving the surface is equal to the number of lines entering it. This is consistent with the fact that no net charge is enclosed by the surface. No net charge is enclosed in the surface itself. So this is the Gauss law. What is Gauss law? Gauss law will be for a closed surface. For a closed surface represented by the number of lines leaving the surface is equal to the number of lines entering it. This is consistent with the fact that no net charge is enclosed by the surface. No charge will be on that surface. Then we can see about the magnetic flux. Magnetic flux formula will be phi is equal to B into A. Phi is equal to B into A. B will be the magnetic field flux and A will be the area. So phi is equal to B into A into cos theta. B into A into cos theta. Here the unit for magnetic flux will be Weber. Unit for magnetic flux will be Weber, and the B will be the magnetic field strength and A will be the area of the given surface, and theta the angle between the direction of the magnetic field and the area vector. Theta be the angle between the direction of the magnetic field and the area vector. So theta is equal to 0 degree. Theta is equal to 0 degree. The angle will be 0. Then cos 0 is equal to 1. Cos 0 is equal to 1. Then phi is equal to B into A. If cos theta becomes 1 in equation 1 means then phi is equal to B into A. Flux passing through that phi is equal to flux passing through the line particular point will be phi is equal to B into A. Then B is equal to phi divided by A. Mark this as equation 2. And if we go for E is equal to 1 divided by 4 pi epsilon naught into Q divided by R squared. So B is equal to phi by A. B is equal to phi divided by A. Mark this as equation 2. And E will be, then the electric field strength E will be is equal to 1 divided by 4 pi epsilon naught Q divided by R squared. 1 by epsilon 4 pi epsilon naught Q divided by R squared. If you integrate this with the closed surface with respect to the surface ds, then closed integral E dot ds will be equal to Q divided by epsilon naught. Q divided by epsilon naught. Here B will be is equal to mu naught m divided by 4 pi r squared. B will be equal to mu naught m divided by 4 pi r squared. Mark this as equation 5. Then we go for the next step. A closed integral B dot ds is equal to mu naught m. Then that is integral B dot ds is equal to mu naught into m. That will be closed integral B dot ds. The mu naught into m value will be 0. If m value will be 0 means mu naught into 0 will gives you 0. So that integral B dot ds is equal to 0. Mark this as equation 6. Then summation. In the case of electric dipole, we can see about the Gauss law for magnetism and Gauss law for electrostatics. Both these things will differ. Okay, this for Gauss law for electrostatic means it will be moving from positive charge. The magnetic fields of lines will be moving from positive charge to a negative charge. If it is for Gauss law for magnetism means it is moving towards from north pole to south pole. It is moving towards from north pole to south pole. And if we go for that electrostatic, Gauss law for electrostatics means it will be closed integral E dot ds is equal to Q divided by epsilon naught. If you go for that magnetic one means integral B dot ds is equal to 0. Integral B dot ds will be equal to 0. So the Gauss law will be of the net magnetic flux through any closed surface will be 0. The net magnetic flux through any closed surface is 0. This is the Gauss law. We have studied. We can apply this Gauss law for magnetism to different different positions, different structures. One is for solenoid, another one is for toroid. Whatever it may be, we can apply this Gauss law for the surfaces. See here, for a solenoid, we are taking the Gaussian surface at the side structure. So it will be of integral closed integral b dot ds will be equal to 0, and if it is for toroid, the Gaussian surface will be of that blue line. See here, or else we can take it in this surface also, in the horizontal surface. This is about the Gaussian. Then we can go for the Earth's magnetism. How the magnetism of Earth behaves. So the strength of the Earth's magnetic field will be of 10 to the power of minus 5 Tesla, minus 5 Tesla. This is the Earth's strength of the Earth's magnetic field. Then we can say about the location of the north magnetic pole is at the latitude of 79.74 degree and longitude of 71.8 degree west in the North Canada. It is in the North Canada. This magnetic pole of latitude and longitude will be in North Canada, and the magnetic south pole is 79.74 degrees south and 108.22 degree in the Antarctica. The magnetic south pole will be in Antarctica and magnetic north pole will be in Canada, and their latitude and longitude is also given. So unlike in the case of a Bohr magnet, the field lines go into the earth. The field lines goes into the earth. Poles near geographic north pole will be north magnetic pole, and poles near geographic south pole will be of south magnetic pole. This is the details. These are the details about the Earth's magnetism. What are the things we have seen? The strength of the Earth's magnetic field will be 10 to the power of minus 5 Tesla, and then the location of the north magnetic pole is at the latitude of 79.74 degree and longitude of 71.8 degree west in the North Canada. It is in North Canada, and the magnetic of south pole is at the location of the magnetic south pole is 79.74 degree south and 108.22 degrey in the Antarctica. It is in the Antarctica. Unlike in the case of a Bohr magnet, the field lines go into the earth. Field lines will be going into the earth, and the pole near geographic north pole will be north magnetic pole. Poles near geographic south pole will be south magnetic pole. These are about the Earth's magnetism. Now we can see about the magnetic declination and dip. See here in this diagram, axis of the hypothetical magnetic dipole, geographic axis. Geographic axis will be little bit tilted. I think you can see about, if you are seeing a globe in a stand, means it will be little bit tilted. There is the geographic axis. That is about the geographic axis. This is south magnetic pole. See here, it is given here. If you are suspending a magnet, it will be on north south pole. Wherever it may be, whatever small the magnet may be, it will be showing the north and south pole only. South pole only, and this is the declination angle of the Earth's axis. See here, this is maximum declination, and this is in the middle will be of the minimum declination. This is of maximum declination, and this is in the north pole, it will be of minimum declination. This will be the equator line, and this is also the maximum declination on south. This is maximum declination on north, and this is maximum declination on south. Okay, this is about the Earth's magnetic field. So the angle of declination is given here from the axis. In the northern hemisphere, the angle of declination will be in this side, and in the southern hemisphere, the angle of declination will be here. See here. The various positions are given. The north pole, the northern hemisphere, equator, and southern hemisphere, and south pole. The declination will be in these positions, horizontal declination. Now we can see about the magnetic declination and the dip. Magnetic declination and the dip. The vertical plane containing the longitude circle and the axis of rotation of the earth is called the geographic meridian. That is the geographic axis. Geographic meridian. The vertical plane containing the longitude circle and the axis of rotation of the earth is called the geographical meridian. And magnetic meridian means it is a vertical plane which passes through the imaginary line joining the magnetic north and south pole. If there is a imaginary line, it is a vertical plane. See here, there is a hypothetical magnetic dipole, that is a axis. So that is the magnetic meridian. The vertical plane containing the it is a vertical plane which passes through the imaginary line joining the magnetic north and south pole. If joining the magnetic north and south pole means it is called as magnetic meridian. So what is geographic meridian? It is the vertical plane containing the longitude circle and the axis of rotation of the earth is called the geographic meridian. If you go for magnetic meridian, it is the vertical plane which passes through the imaginary line joining the magnetic north and south pole. So the magnetic meridian at a point makes an angle with the geographic meridian. It will be making making an angle with that of geographic meridian. Magnetic meridian will make an angle with that of the geographic meridian. So the angle between the true geographic north and the north shown by a compass needle, this is called the magnetic declination. That is called as the magnetic declination. So the declination is greater at higher latitudes and smaller near the equator. The declination is greater at the latitudes and smaller near the equator. The declination is of 0 degree 41 minutes at Delhi and 0 degree 58 dash west at Mumbai. The angle of declination will be 0 degree 41 minutes at Delhi and 0 degree 58 minutes west at Mumbai. So this is about the angle of declination. So far today we have seen about the properties of the magnetism and properties of magnetic lines of force, and then magnetism and Gauss law, and about the Gauss law and Earth's magnetism and magnetic declination and dip. Magnetic declination and dip. Students, learn these things, see the video, learn these things and write fast.